Road to Olympiad.
Welcome to RTO. Consider the following problem. Prove that for every positive integer k, there exists a positive integer nk, such that square root of 3 minus square root of 2 the whole thing to the power of k is equal to the square root of nk minus the square root of nk minus 1. There are plenty of square roots here, so we might need to try getting rid of it in order to get the integer nk. But the problem here is we need to show that for every k, nk is an integer. In fact, we'll attempt to find nk in terms of k, and then try showing that each of those nk that we found are all integers. Pause the video if you'd like to give this problem a try, and when you are ready, keep watching to learn how to solve it. To solve this problem, we start by noticing that by getting the reciprocal of the given equations, we can rationalize the denominator by multiplying their respective conjugate pairs. The nice thing here is, upon simplifying the denominator, we notice that each of them simply give us 1. Therefore, we have square root of 3 plus square root of 2 the whole thing to the power of k is equal to the square root of nk plus the square root of nk minus 1. Adding the equation we obtained just now with the given equation in the problems, we have 2 square root of nk is equal to square root of 3 plus square root of 2 the whole thing to the power of k plus square root of 3 minus square root of 2 the whole thing to the power of k. Dividing both sides by 2, squaring both sides, and factorizing the 1 out of 4, we have nk is equal to 1 out of 4 times 5 plus 2 square root of 6 the whole thing to the power of k plus 5 minus 2 square root of 6 the whole thing to the power of k plus 2. Here we obtain nk in terms of k, and like what we mentioned just now, we are going to show that each of these nk is indeed integers for every positive integer k. To do so, we can let xk to be equal to 5 plus 2 square root of 6 the whole thing to the power of k plus 5 minus 2 square root of 6 the whole thing to the power of k. So in order to show that nk is an integer, it is equivalent to show that xk plus 2 is a multiple of 4. Recall that the general formula for the recurrent relations xk plus 2 is equal to a plus b xk plus 1 minus ab xk is xk is equal to a to the power of k plus b to the power of k, which is something similar to the xk that we have. So we know that our xk satisfy the recurrent relations xk plus 2 is equal to 10 xk plus 1 minus xk, with x0 is equal to 2 and x1 is equal to 10. It is not difficult to conclude from the recurrent relations by using induction that each of the xk must be an integer for all positive integer k. This is because each of the terms is basically the difference of two integers xk plus 1 and xk. What we left to show now is only that xk plus 2 is a multiple of 4 for every positive integer k. We are going to show this again by inductions. Assuming that xk and xk plus 1 are both equal to 2 mod 4, then xk plus 2 is equal to 10 times 2 minus 2, which is equal to 18 mod 4, and this is equivalent to 2 mod 4. Therefore, since x0 and x1 are known to be 2 mod 4, so by induction it is clear that each of the xk is also equal to 2 mod 4, and thus our claim is true. Hence, we have for every positive integer k, nk which is equal to 1 over 4 times xk plus 2 is an integer. And this marks the end of our solutions. Post in the comment below if you have any thoughts on the video, and if you haven't subscribed yet, consider subscribing. This will really help us out. Anyway, see you in the next video. Thank you.